Okay, so I am going to show you how to determine the change in electric potential or the electric potential with respect to infinity due to just a single point charge. And I'm going to do this without calculus. Instead, I'm going to use a numerical calculation. I'm going to do this in Python. Okay. So let's have a quick review. What is electric potential? So suppose it really has to do with electric potential energy, which has to do with the work done by an electric field. So when you have the work energy theorem, the work energy principle, if I calculate the work done by something and the work does not depend on the path, then I can actually move that work term to the other side of the work energy equation and make it an energy, but then it becomes negative. So the change in electric potential energy is negative the work done by that force. And then what about the electric potential? The electric potential is just the electric potential energy per unit charge. And that way we don't have to worry about what charge is there and whatnot. It's just the potential, okay, in volts. So let's start with a constant electric field. Suppose I'm right here at point 1 and I want to move to point 2. Well, when I move that way, the electric field is a constant electric field. It does work on the charge. And it would do some positive work to increase the energy because the force and the displacement are in the same direction. I could instead consider this as a negative change in potential, which I could calculate by taking the work done, which is just the charge Q times the vector E, and then dotting it into the displacement vector, and I get this negative QE delta R cosine theta. Theta is 0, so I just get negative QE delta R. And that's how I would find that change in potential energy, divide by the charge, and I get the change in potential. And this is true for any constant field where theta is the angle between the displacement and the field. So we can do that. I can calculate the change in potential in a constant electric field. It's just negative E dr delta R if they're in the same direction. That I can do. Okay. But what about a point charge? Here's a point charge. Suppose I start right here at position 1 and I'm moving this way. If that's the case, there's a problem in that as I get closer and closer to this charge, the electric field gets larger and larger. So it is not a constant electric field. And in fact, this is the expression for the electric field due to a point charge. It decreases with r squared. So if I'm moving closer, it's going to increase. So how do we do this? Well, you can do it with calculus. But we can also do it by breaking this into tiny little steps. If I go from here just to there, just that small delta r, then the electric field is fairly constant, and I can pretend like it is. And if I do that, I can use the previous equation. I could say, well, the change in electric potential is negative E delta R cosine theta. And in this case, theta would be 180 degrees since I'm moving in the opposite direction as the electric field. And then I can do it again. I get that change in potential. And then I could go for the next little delta R and so forth. And so breaking this into small steps, going from point 1 to point 2, gives me incremental changes in potential, and then I can just add them all up. And that's what I'm going to do. Now, if you did this if you look in the book, you're going to see this is the expression for the electric potential due to a point charge. This is the potential with respect to infinity. So if I start an infinite distance away and move to a distance r, then the change in potential is kq over r. So I want to show that this works with my numerical calculation. So I'm going to start from here. I'm going to have a small delta r, and I want to show that this works. I'm not going to start at infinity because that's not realistic. I can't actually do that. But I want to calculate during each step. This is my change in potential. This is kq over x squared. I'm dealing with the x direction. That's the magnitude of the electric field times this delta x, how far I've moved, and then it's going to add that up each time. It shouldn't be too bad, so let's get started. So I'm going to start with I want to do this for a 1 nanocoulomb charge. So I've already put in here K, my Coulomb constant. That's my charge, and my starting position, 10 meters. Remember, this does not deal with units. I have to include that myself. So now I need to find my step size. So I'm going to say dx equals 0.1. And I want to also say v equals 0. V is my, I'm going to keep adding my potential to this. So I get the total potential. But I'm going to start off with 0. And then I want to say r equals, let's say 0.5. This is where I'm going to end up. So what I want to do is say while x is greater than r, because really I'm starting farther away, I'm going to keep moving until I get to r. The first thing I'm going to do is calculate the electric field, the magnitude. This is all in the x direction. So I get E is k times q divided by x squared. So remember in Python, squaring is star star, not hat. Right? A lot of people get mad about that, and I don't know why it is, but now I can calculate based on that electric field, assuming it's constant. I can use my constant formula. So I'm going to say the change of potential over this small step is E times dx. So dx is my step size, E is my electric field. And it's a positive change because I'm moving in the opposite direction of the field. Now I'm going to just add this to my electric potential. So I'm going to take my small step size and add it to what my potential was before. And remember, this is not a normal equal sign right here. This says make it equal to. This says take the potential. I didn't mean to do that. To add the delta V that is calculated and make that the new potential. Okay, so those V's don't cancel. Now the next thing I need to do is move my x position. So I can say x equals x minus dx, going to be closer, and then that's it. And let's just do this. Let's print. Here is my calculated V based on this, and it will be V in volts. And just for comparison, let's print the theoretical V, and that's going to be equal to K times Q divided by R volts. That's the equation. And let's save that. Let's see. Numerical, not numerical, numerical V example. Save. Save. And now I'm going to run it. Okay. So that actually gives a fairly close answer. Surprisingly close. Okay. It's not perfect, right? Because what's happening is I'm starting far away, and I'm ignoring from infinity to 10. Okay. Let's just see, what if I increase this to 20, and so I start 20, which is not infinite either. Oh, it's even further away. That's weird. Okay, let's see. Let's make the step size smaller. Okay, there you go. I'm happy. It's not perfect, okay, but I'm happy. You can play around with this, and you can make, one of the things you could do as you get closer, the electric field changes much faster. You can put a thing in there to change the step size as you get closer, but I'm going to keep it simple. I do want to do one other thing. Let's make a graph. So I'm going to go up here, t graph equals type graph, and we're going to plot the x title is going to be equal to distance, let's say position, in meters. And the y title is the potential with respect to infinity, but I'm not going to put that because I'm lazy, in volts. Okay, now let's do two graphs. F calculated, it's going to be a type G curve, color equals color.blue. And let's give the label of calculated. And let's make another graph. FT for theoretical, G curve, color.red. And label equals theoretical. Okay, so now down here, I need to calculate. I'm going to plot these. So the first thing I need to do is calculate the theoretical potential, VC. And let's say that's K times Q divided by X. Yeah, that should do it. And now I can plot them. So FC.plot is going to be X coordinate of X and the Y coordinate of V. Yes. And then FT.plot X and VC. Let's see what happens. I should save it, shouldn't I? Okay, run it. Excellent. Okay, so you see here that the two curves, and I did put the label over there, are very close together. Okay, and they match fairly well. So I'm pretty happy with this whole thing, but you can see they're not quite the same. I use poor values here, but this is really just not, it's just to show you where that comes from. Okay. All right, so there you go. I'll include a link to this code down below for your viewing pleasure, and you can edit that and play with it yourself and change the numbers. We'll do some more physics later. I'll see you guys later.